Thank you, Ian. So first, it's a pleasure to be here in WISE, and I'm not saying it just as a courtesy. It is really a pleasure to be here. So it's a great community, and we can take a millisecond to understand how fortunate we are to do this stuff. And today it's kind of a more a keynote to kind of get people to understand a bit about infragravity. And I had a great segue yesterday from Ad. He's here somewhere. Yeah. And so, but Ad spoke a lot about the nearshore. We will speak a lot also, but we will try to think about it in a more kind of broad perspective on the field, so cross field in many aspects. Okay, without further ado, let's see if this works. Okay, so what are infragravity waves? So let's call them the and low frequencies oscillations in general. So if I see a spectrum, and that's measurements of acoustic surface tracking from an ADCP, its pressure cell outside of Haifa port, and this measurement it's with a sonic within Haifa port in one of the piers. So if we look at this area, that's the area we are used to as like the surface waves, yeah? So we of course see that the pressure is a bit attenuating here, and we see kind of a nice spectra, normally looks like a John Swab spectra. So if we kind of parallel it to music, yeah, this will be the guitar player, yeah? That's what we are used to see, that's what our ears are used to listen to, because we listen to, our ear is tuned to human voice, and that's what we are commonly looking at. And then there is this area of around 100 seconds, between 25 to 250, we define it, we can talk about that. And this is the area that in music will be the bass player, yeah? So they called it a surf beat, yeah? So a surf beat relates to the surf, and it still has a beat, and that's exactly the position of the bass layer in the band. It connects the melody to the beat, yeah? And the beat, its lower frequencies, is kind of sitting here, and this will be kind of let's say low oscillation, shelf oscillation, shelf tides they call it, and all kind of stages in field. So it can be like let's say 30-minute or 40 or 50-minute oscillations in the basin. Yeah, so this is kind of using the deep to intermediate water, so you use dispersion relation, and this area is normally also part of this, depending on the depth, but a lot part of this is normally kind of considered shallow water. But you have also infragravity in the intermediate. So infragravity waves. So just it's a kind of a tutorial, so you can stop me with questions anytime. Feel free. Infragravity waves, so we define them 25 to 300 or 25 to 250. Wavelengths between a kilometer scale to tens of kilometer scale, small tens of kilometers, so you can have these waves like 15 kilometer propagating in the ocean. So they are kind of closer to a bit tsunamis or meteo tsunamis sometimes. Very high speeds like can be in the deep water, in our deep water for surface waves, but not deep water for them. And their importance for harbor and basin resonances. So they can oscillate if the scales are a few kilometers. You can have a port, and then you have some kind of a pier area, 3 kilometers. They can seize inside, and then they really bother ships. They can alter the breaker-liner location, so affect sediment transport. They affect satellite altimetry, and we show something that Fabrice was doing there. You can see him here, he's a star of this show. And you can have like breaking ice sheets, and they even generate Earth's hum. So that kind of we see them on the bottom of the ocean and sonograms and the thing that I wasn't aware apparently lately, they actually oscillate and generate gravity waves in the atmosphere. These are waves that just propagate upwards, and what they do, they actually mix the atmosphere. So they have an effect on mixing the atmosphere even. So you wouldn't think that these waves are so key connecting things, but they are there. Let's just inspect port agitation, harbor agitation. So if you see a port, this is a Haifa port, it's like a body of a guitar, yeah? So there is an entrance and wave gets inside. And if we close this and pick the strings, we won't hear much, yeah? But if we have this resonator here inside, and it gets inside, so every wavelength will fit part of this and will be amplified, and then we will hear the sound. So same with the harbor, just we try to plan it in the opposite way, that it will dump the waves. We don't want them to oscillate and resonate inside, and then you actually need to plan a harbor according to the infragravity wave regime that you have, and that's kind of a challenge, yeah? So, because many times we don't have enough measurements, and we will talk about it, and we don't have actually a full understanding on all the generation mechanisms of these waves. So if you think about a ship, if you think about that's like a resonance situation, so that's you push the kid and you do it a lot when you start being a young parent, and then you think about resonance because you are a scientist, and the same thing happens actually with the ship inside the port. And the ship, if you think about it, is a mass and spring, yeah? So it's just you push it down, it will jump up. It jumps up, it falls down, yeah? So it has natural harmonics. And these ships have natural harmonics. They're also moored to the base. So if you are getting to their natural harmonics with these waves, you have a mess in loading them, and you can break, I don't know, the decks of the ships, and they can resonate with their moorings that are also springs and sway to the port. So that's kind of important for harbor design. Even if you have the harbor, just to design what is the stiffness of your mooring system, yeah? Just not to make it resonate. So the basic kind of generation mechanism is nonlinear shoaling. And in nonlinear shoaling, we go to much simpler thing. You had all this crazy cubic interaction. We are in tried interaction. Just in one hand, it's simpler because we are just in quadratic nonlinearity and not cubic. And you have tried interactions and not four. In the other, you have a changing bathymetry, which kind of what allows you to solve this resonance. So let's see how it works. So I really took out most of the equations of this talk. So these ones we know, yeah, it's like a potential flow, and we have like nonlinear components, and this writing this kinematic and dynamic, that I'm sure you all know this equation, and writing this kinematic and dynamic boundary condition on the moving surface actually gives you an infinite nonlinearity series if you write it as a Taylor expansion. So even just the first one, what are the quadratic interactions doing? So if we look at this and we say, okay, we first have a linear system, and we just make a Fourier series and say every component propagates like the known, first class in marine engineering solution or water wave, and they are propagating on a flat bottom. You can write every frequency, which is every frequency being in the spectrum, you can write it as a what we call the Miles-Slope equation, but maybe that's a bit too complicated. Let's erase this crazy stuff. So you can write it as yeah? Oh. Maybe we can silence it, but I guess somebody was excited about Miles-Slope. Yeah, Miles-Slope, I know this. Yeah, okay. So that's even simpler. That's Helmholtz. So Helmholtz common also in acoustics. So Helmholtz equation, and you have a Helmholtz equation for each frequency. So you have omega, and you know that this will be through dispersion relation, and you have a Helmholtz equation for every frequency. And if you think about it, that's just a second order. So you don't even have this attenuation, just a mass spring problem. Yeah, it's a second order problem and a mass spring, and each way of this spring kind of relates to the omega, and k will be kind of the stiffness of the spring. So every spectral beam is like a mass spring system. Okay, but we have nonlinear effects, yeah? So this is a second equation. We know it from high school, so that's okay. So it's basically if you multiply a sinus, that is the solution of this harmonic oscillator, by another sinus, and you have the sum of all of them, so each multiplication of these crazy sinuses will give us, so wave in frequency A times wave in frequency B will give us the wave in the frequency difference. We are scientists, so we call it subharmonic interaction. Yeah, fancy word, but high school math. And superharmonic interactions. Yeah, the sum of this frequency. Okay, so that's kind of, so we have this crazy nonlinear mild slope component with all kind of sum with this quadratic interaction, but let's make it simple because we don't like it complicated. So yeah, much simpler. Okay, not that much. So let's think about it as the mass spring. So basically what you have is all kind of interactions with all other spring. So maybe two of these springs will interact and put a force in this one, and two of these springs will interact and put a force in this one. They just transfer forces between each other. So what do we know about springs that we force? Let's just look at one spring that we force. Yeah, what do we know about it? We know that we can force it, just force it, and it will oscillate according to it. So you have homogeneous solution of its oscillation. And a forcing, if it's not its solution, you will just also have a particular solution that shifts it. So that's a forced oscillation. And you can have another option that you force it in a frequency that exactly excites it. And if you excite it, you create a resonance interaction. And when you have a resonance interaction, then things really start being interesting because you are starting pushing energy between spectral beams. Yeah? So otherwise, the spectral beams will just play back and forth with each other. They transfer here, they transfer there, but it's always oscillatory. They will always bring it back in this concept if you look at the spectra. But so this is the first case if you have non-resonant condition. So one harmonic will be one harmonic, omega 3, you can sign it here, will be a plus or a minus of the other. And the same will be in wave number space, but we are in 2D, so we need it as a vector space. And you have a nonlinear relationship. So these three ones, if this sum works, even in 1D, you say, there is a nonlinear relationship, we have a problem, this won't work. Yeah? It won't close to zero. So that's why they say deep water, no resonance conditions. Okay, just force. I didn't start my clock, so you tell me how much passed, yeah. Oh, wow, I need to be faster. Okay, so that's a forced oscillation, and that's what we saw with Ad yesterday, that we have the wave group, and if we have two components sinusoidal very close to each other, then they generate a group, that's a linear, and in the nonlinear part, we will have this kind of depression where the group waves are much higher, and that's kind of a bound wave that is an infragravity wave, because it's a very, very small wave number, yeah? So these bound waves, forced waves, and this is the Hasselmann paper 62, and that's crazy equation, but basically what he did is just saying, give me a full spectra and I will give you all the bound wave correction for everything. So that's it. That's Hasselmann 62 in the area that is still digestible, then you continue, it gets much crazier. And then what happens when you have resonance conditions? How do you close a resonance? So they put us this and they say, that's a Bragg resonance. There is a bottom component. What is a bottom component? So the concept is like this. This oscillation that multiply each other, yeah, have a coefficient, yeah? And if this coefficient it is constant in deep water, so nothing happens. But if this coefficient starts oscillating, then we have a resonance because it adds another thing and can add up and close this resonance condition. But why should your coefficient resonate? Yeah? Why should not resonate, like oscillate? So you can think about it like this. If you have your coefficient is function of your depth, yeah? So if your depth is a linear function and you just write it as a Fourier series, a linear function has all Fourier components, and one of them will resonate as a Bragg resonance. Yeah? So basically, the change of the bottom will close you, if you look in Fourier in Fourier glasses will close the resonance. And that's how it looks in 1D. That's a superharmonic, that's a self-interaction. So we took two of them. And we have two omegas, so the omega 3 is kind of defined, and then we can plot through dispersion relation the circle around it, and this should be the length of K3, but K1 plus K1 won't become K3 unless you add up a bottom component, and then you close the resonance, and that's a kind of self-interaction. That's why you see the second peak in the spectra, because that's how the energy transfers there. Subharmonic is the same, omega 2 minus omega 3. You will get omega 1, you plot the dispersion relation, and then you need a bottom that kind of helps you closing this resonance. So I will push a bit forward, yeah? But what happens in shallow water? In shallow water, we know square root GH, that's the wave phase velocity. So omega divided by K, if everything is shallow, it's always square root GH. So it's a linear relationship between omega and K. So if you close 1D resonance in omega, by definition, you close it in K, okay? And this sounds kind of trivial, but this was blocking the community for quite a few years, this separation between these two concepts, yeah? So here you don't need a bottom component. And then it can actually go to any order, yeah? So you can have the cubic interaction resonating, everything resonates, and then you have a boom like of the shoaling of transfer of energy near shore. So I will just skip here. So a wave action, so Theodore is here, this is part of his PhD work. And then we kind of said, okay, we have this as deterministics, and we actually wanted to have a source term NL to contain all these nonlinearities, also for models fitting WaveWatch and such models. So here you can see the stochastic model. That's kind of the linear part of the wave action equation. So you can see the change of wave action, and just in quasi 2D, the change of the horizontal change. And in the right side, so that's the wave action. That's what's written here. So in the right side, because we multiplied with an amplitude in order to create on the left side a wave action and not just an amplitude evolution in the term deterministic. So in the right side, we have a body that is called here the bispectra. So if this is the spectra, A times A complex conjugate, this will be a bispectra. Yes, so you have three components of waves playing with each other. And you ensemble average to throw away all the phases, because we don't like phases, because then Nyquist hit us in the head and say, hey, you need a grid very, very small. So we want to avoid phases. So we just can write frames that are in a kilometer scale instead of a few meter scales, yeah, your meshes. So we did this process, and we lost all phases, and now we have a stochastic. And then there is a lot of play that I won't get because it gets to the math like what we saw in there. But the concept is that you will have a bispectra, and then you say, how do I calculate the bispectra? So you say, okay, let's write an evolution for the bispectra. And then you have an evolution for the bispectra, but on the right-hand side, you suddenly have a trispectra. And then you think, maybe I write an evolution to the trispectra, and et cetera, et cetera. It never ends. So what do you need? You need a stochastic closure that relates higher order moments like that to lower one. And then you basically transfer this trispectra for interactions just to say, it's just double the time. I'm using just doubles of the original spectra. Instead of all possible permutation, I just say, within these four, I just equate two of them, and they are just interactions of spectra. And then that's the stochastic closure, because I write here spectra, and then I have F here and F here, and a wonderful equation with millions of equations to propagate, and we never do it because it's too complicated. So we can do it just for testing. Okay, so what is the procedure in order to get a source term here that is digestible? So that was kind of changing in the community, and there is the works of Eldeberki, they just neglected changes in the bottom, this flat bottom approximation. This doesn't change, and then we can just relate B to the spectra and push it, substitute it here. And there was also an extension of it with all frequency, because Eldeberky was for the second and fourth peak. And Beck-Girard, where is Michel, is here? Yeah, so Michel, they derived this concept and did it with all interactions, so it was fitting also for infragravity. And what we did in this PhD was basically saying, okay, you have the area that the bottom changes, you have the area that it's flat. Let's really solve this as a differential equation. And this was done already by Agnon and Shermet. Agnon was my PhD supervisor before. But we kind of localize it in the way of Miki Shtiasny, also a prominent scientist in the field, and basically divided, and this was the new thing, to these new fields, and managed to do, because you have integrations here for oscillatory function, we did a process that's called localization. So we just get local energy, and then we can say, okay, we have something much simpler that we can push here and say that's a S3 and L source term that should fit for the whole nonlinear Scholem. So this was done in this paper, which kind of discussed that the bottom is affecting the coefficient. The subsiding paper just says, it's not just the bottom, waves are breaking in the nearshore region. So actually the bispectra is changing, so we took care of all this guy. And okay, we have a source term, what can it do? So we tested it back then, that's a bichromatic experiment, 2 waves propagating, Scholem in a flume. This specific one was not published, but specific case, you can see the paper 2006, but we got the results of the data for the bichromatic. They showed for Jones swap, etc. And then we see that this is the spectra, this is like the free infragravity wave generated, and with a stochastic source term, we can generate this infragravity wave in Scholem. Okay, so how will it be in measurements, this thing? So if we look these 2 waves in the measurements, we can point this 11-second and 11.2-second waves, and poof, they transfer energy to the difference, which is a 616-second wave. It's, I guess, a bit out of the infragravity that we measure, so I need to kind of make it. But what you see here, and that's interesting, that's within the port. And you see this peak, and this peak is exactly resonating with your the scale of this pier. Yeah? And that's why we have much more energy than we have in the deep water. Yeah? So that's an interesting kind of this. Maybe we should publish it, but like that's kind of the concept of planning ports. So what happens if you are in 2D? So in 2D, what will happen is that you have a subharmonic interaction. Let's say omega 6 minus omega 5 equal omega 1. So omega 6 times delta omega 5 times delta omega will make 1. And then you plot the circle around this vector coming out. They are both in the same direction. And you see that this is the bottom. And you will have wave generated in an angle. Yeah? So that's a blow up of this. And the infragravity wave is generated in an angle to your wave. So your wave is Scholem. They are getting straighter to the shore. So they are reducing the spread. Yeah? But the infragravity part, poof, shoots aside and actually extending the spread. So your infragravity spread, oh. So, okay, so that's how it will show. We did like, that's a Boussinesque solution, that's our solution. And then we can see, okay, let's say they are reflecting, and that's a WaveWatch model. WaveWatch model that we run, and we added a reflection term from the bathymetry. It's like solving the Milesop equation, and it's actually reflecting without a shoreline. So here is a flat 100 meter, let's say it's the shelf that's going down in a slope of 10%. And then you can see the waves propagating out from this side, let's say the infragravity wave, and they're refracting back. But if you have a reflection from the bathymetry, everything works differently. and you see all this area is also covered with energy. So a lot of more energy will be trapped inside. So that's our free waves, and I encourage whoever doing to implement this. We implemented it for WaveWatch. So another type is an edge wave. So another type of solution, just wave propagating along. It's a solution of the shallow water equation. So we have all these types of waves. Yeah, free waves, all kind trapped, incident, blocked, bounded, edge waves. How do we measure this in situ? So we either put a lot of sensors, and that's kind of hard because they need to be synchronized and they need to be in a very large span because these are very large wavelengths. And we have, and then we can form a K omega kind of spectra and try to understand which is which. There is another method by Arjun. Yeah, I have 45 minutes. Are you sure this is already 10 minutes before? Yeah. Okay. No, we started. Okay, good. So I will jump. This was too much tutorial. Okay, but that's important too. Okay, so so another way, Matsuba et al. Kind of using a lot of components of an ADCP type and can generate some kind of free wave, bound wave separation. And Fabrice was kind of discussing making it for the large scale and saying, okay, the free waves are important. We don't know yet how to generate them with this SNL stuff. So let's kind of create a more empirical way of creating this energy and pushing it into the model. And that's what they did. And actually, with a work of art, they showed that in the North Sea, these waves are much more prominent than we thought. Yeah, we have a lot of free wave energy, and then we need not to just shoal waves, but also think what comes from the free spirit. And that's a courtesy of Anne, that you can see that if you have significant wave getting in, and you have this Fabrice sortum generation, it just pushes infra-gravity when it gets. So you get generation in a distant shore, and then energy is being pushed also to the basing and kind of affects your overtopping or whatever calculation you do. IMU or sensitivity scale consideration, you can see that's a buoy of, and that's these two are like the acoustic surface tracking and a pressure cell, and you see that the buoy is actually decaying after 25-30 seconds, so you don't get much energy, and you see differences between the acoustic and the pressure, which you won't expect. So why are these differences? Because you are integrating for long times, and your and your temperature is changing, so your velocity of sound changes, so your tracking of the surface is affected. So there are different time scales here, also for the altimetry. And if you see a spotter buoy GPS, we see all this area already in 15 seconds is not being compared that well. Yeah? So that's a problem. Okay. Can we extend buoys? Sorry. Can we extend buoys to the IG range? So everybody knows that what moves the buoys is actually this guy. We know it 3,000 years ago. And then we say, we want him to move the buoy, but he was occupied because there are a lot of buoys now to this day. So let's say we are modeling. So we just model this arm. Yeah, and this is his arm in the lab, and that's a storm in front of an ADCP measurement, and actually we want to just test. So whoever has accelerometers or something that want to test, we want to test in real condition. Can it measure our buoys the conditions of infragravity waves? So that's a storm, as you can see. That's what he does, but we don't have him for the job. Yeah. So another special scale consideration is that we have bathymetry, and that changes the waves. So can we really do wave number Fourier transform and expect everything to look like sinuses in large scales? I don't know, and we need a new way maybe to do it. Another thing, and that's thanks to Nick Pizzo, I don't know if he's here, but he dug up this paper from '82, and these waves kind of reach bound, and that's deep water for these waves, and they reach the shelf. And actually some, because the bound wave solution is different here and here, they actually just reflect free waves to both sides. So we have other problems. So if we are looking in areas of changes, we will have other problems of free bound wave to free wave exchange and extra stuff like that. So other maybe deep water generation. So there is a paper about generation using tides, also not implemented to a model. And another work of ours that says, let's kind of push it a bit forward and say, even in deep water, maybe if just the bispectrum changes, we can have resonances. And actually, we found such resonances because of wind gusts. Yeah, I will skip this. These are two peak spectrums that also Babanin and Noze saw.
Yeah,
and
that's just it.
Okay, so I will skip that, but I will just want to say that we need a community effort here. There is so much to do in order to create a real wave model and real enough measurements to test it in order to kind of make such an operational model. So, we have a group of young and energetic people, and we kind of want to push this forward. So whoever is interested in this, want to change, we want to create one a first meeting that relates only to infragravity and maybe write a cost action for collaborating between people. So whoever is interested in this direction, just talk to me, and we have another initiative that we are already running. So, so that's kind of the idea, and so community for Recrite. So thank you for listening. And I can say about the discussion of yesterday about a paper that's a picture I took after deploying first time deep lev mooring. And this data set of almost 6-7 years is available open source for everybody in the deep sea of the Mediterranean if you want to use it. So that's continuing a talk I had before. So thank you very much.